This is my project 1.4 counting circuit. This project consists of 8 parts, each adding on to the last. This is the NAND gate oscillator. The circuit uses input values from gates inside the chip to output certain values that power the circuit. The NAND gate oscillator powers the rest of the circuits in this project by providing a square wave clock signal. This circuit uses a pull-up resistor to ensure when the button is not pressed, there will be two 1 inputs on the first NAND gate. Using NAND logic, we can determine that these two 1s create a 0 as an output. This 0 carries over to here. We know that any 0 input creates a 1 output. These 1s carry over to here, outputting a 0, and this 0 carries over to here, outputting a 1. Since this 1 is here, we know that there is no potential difference, so this LED can't turn on. This 1 comes up here and charges this capacitor, comes down here, and plugs into the second input of the second NAND gate. When the button is pressed, these two inputs will become zeros, outputting a 1. This 1 carries over to here and outputting a 0. This 0 carries over to here and outputs a 1, and the 1's here, outputting a 0, allowing the LED to turn on. This 0 up here allows the capacitor to discharge, putting a 1 here. Eventually, the capacitor will run out of energy, making this a 0. Now that this input's a 0, this 1 will become a 1, carrying over to here, outputting a 0, carrying over, and putting a 1 here, meaning the LED turns off again. This 1 will flow up to here, charging the capacitor once again. This is where the cycle allows the circuit to oscillate, and the LED will keep turning off and on again. The decade counter uses a 4017 chip that uses the clock signal from the NAND gate oscillator and adds one to the counter for each rising edge signal. This chip has a divided by 10 output that makes the display count at 1/10 of the speed that the NAND gate oscillator oscillates. This is the binary counter. This uses the 4516 chip that counts from 0 to 15 using the inputs given from the decimal counter. This chip counts at 1/10 of the speed of the binary counter because of the clock input being the output of the 4017 chip. This circuit converts digital inputs to binary inputs. The presentation of these binary outputs is represented by 4 red LEDs. Keep in mind that the 4510 chip is the same as the 4516, just that the 4510 counts from 0 to 9 and the 4516 counts from 0 to 15. This is the 7-segment display. Once again, the clock output from the NAND gate oscillator powers the 4511 chip. The 4516 is now replaced by the 4510 in order to reduce lag when the 7-segment display switches from 9 back to 1. Also, the 4511 chip takes 7 inputs from the 4510 that are derived from the 4 binary inputs. This is how the 7-segment display receives its output signals to power the corresponding numbers. The PCB version of the circuit consists of one custom PCB, one 0.1 microfarad disc capacitor, one 100 microfarad electrolytic capacitor, one 14-pin IC socket, three 16-pin IC sockets, two 1 kilo-ohm isolated resistor networks, and one 2-position 2.54mm terminal block. Since these parts are soldered on the bottom of the custom PCB, the battery requires a coating of electrical tape in order not to short the circuit. This is the fully constructed PCB. The case fully encapsulates the battery, with the terminal block feeding the wires from the battery into the circuit. As you can see, the PCB version is able to count up and down. In my final breadboarded prototype, I decided to replace one of the resistors in the NAND gate oscillator with a potentiometer in order to alter the rate at which the circuit oscillates. Changing the core clock signal of the circuit allows me to adjust the 7-segment display to count faster or slower. I did this by replacing the 1 megaohm resistor with a potentiometer. Since the potentiometer's max resistance is 10K, I needed to upgrade to a 10 microfarad capacitor in order to match it. As you can see, the circuit is able to count really fast and slower than normal while still being able to count up and down.